Found, found a paper. Okay, you found a question paper. Okay, just a minor correction. This is a simple harmonic motion. Question 4. The vibration generator in B is switched on and its frequency F of vibration is gradually increased from 0 to 10 Hz. Sketch the variation with F of the amplitude of the oscillation of the ball. First, we have to determine the resonance frequency, which we have determined earlier, the previous question. You cannot draw like that, right? Because they say from 0 to 10, even though they don't give a mark, they don't penalize you. So you have to, it doesn't go to 0, same as this side. Right? If you prefer, you can draw this way. Okay, be a bit louder, cannot hear you. Okay, Number 5, define electric field. Yep.
Force per unit charge acting on positive charge.
Force per unit charge or force per unit positive charge. Okay, on figure 5.1, figure 5.1 shows two parallel conducting plates that are in vacuum. The plates are separated by a distance of 6.7 cm and have a potential difference of 330 volt between them. On figure 5.1, draw 4 lines to represent the field between the plates. Just draw 4 lines. Right? Be careful, they are parallel. What the examiner will look for? 4 straight vertical parallel lines, approximately evenly spaced. Arrow downwards. That's how you get a 2 mark. Determine the electric field strength of the electric field between the plate. V over D. And earlier years from 2022, they more or less test uniform field. But from 2025, I think they are testing you, go back to the old place. Non-uniform field. Sometimes they may combine electric field and magnetism. An electron travel at a speed of 2.6 times 10 to the power 7 meter per second towards the region between the plates, as shown on figure 5.1. Draw the path of electron as it moves between and beyond the plates. Right? This part is a straight line. This part continue the straight line, and then this part parabola, and then this part a straight line.
Going outwards.
Straight upwards. A uniform field is now applied to the region of electric field, figure 5.1, so that the electron travels undeviated through the region. determine the direction of the uniform magnetic field. Okay, how are we going to do that?
Fleming's left-hand rule.
Magnetic force is downwards. Right, this is an electron. It's attracted upwards, then positive plate is upwards. So the force is upwards. So the magnetic force must be downwards. So using Fleming's rule, right? Remember your Fleming's left-hand rule.
Into the paper.
Say a bit louder, can you hear?
Yeah.
Okay.
Just now I was into the page.
Explain with reference to forces exerted by the two fields on the electron, why the path for the electron is undeviated. Okay, you want to try?
The forces are equal in magnitude, but they act in opposite direction.
Okay. Forces are in opposite direction. 1 mark. Electron is undeviated when the magnitude of the forces are equal. Determine the flux density B of the uniform field. Give a unit for your answer. Okay, how are we going to solve that? Yep, how are you going to solve that?
See, it's something to do with B equals E over V.
Right? They take you through step by step. You already got the answer here. Magnetic force equals to electric force. Cancel our Q. And then B is E over V. E we have calculated earlier. And then the speed you can get from the question, previous question. Okay. You should be doing it and then using the marking scheme to mark. And you should see yourself improving all the time. Figure 6.1 shows a capacitor of capacitance C connected in series with a resistor of resistance R. Initially, the switch is open and there is a potential difference of 12 volts across the capacitor. At time t equals 0, the switch is closed so that there is a current I in the resistor. Figure 6.2 shows the variation of current with time. Explain the shape of the line in 6.2. You want to try?
PD across capacitor is proportional to charge on the capacitor, and the charge on the capacitor increase.
Right? Basically, this one summarized for you. PD across capacitor is proportional to the charge on the capacitor. Okay, that's PD. Proportional to the charge on the capacitor. Current in resistor is the rate of decrease in charge on the capacitor. Basically, current, there's a decrease of rate of decrease. Charge is proportional to current. Charge is proportional to current. That's how we derive it, but you don't need to know that. Except you have to express it in words. Charge is proportional to current, so that the rate of decrease of current decreases as the current decreases, therefore exponential shape. So 3 marks, 3 points. Okay, alternative answer by giving by marking scheme.
Okay.
Use figure 6.2 to determine how to determine the resistance. Yep.
R equals VOI.
Right? You have told initially is 12 volt. So that's the initial current. No? The initial current. So R is VOI. V is 12 volt. Initial current. Right? 0.13 times 10 to the power minus 3. Remember milliampere. Don't forget that. Convert to SI unit. Time constant. How to calculate the time constant? Yep. How to calculate time constant?
Current equals to original current I naught E exponential the power of negative T over.
Okay, you can remember, good. If not, use this formula. Replace the X with I. Right? I equals to I naught E minus T over tau. That's a time constant. Then initial current is 0.13. So we learn it. Right? The easiest way is to take this point. 0.02 and then 8 seconds. That's your 8 seconds. Take this one down. By I 0.02 divided by I naught. And then we get this one and complete the calculation. Okay, stop me if you need to explain further. Use your answer determine capacitance. All you need to remember is this is calculated, and then the time constant equals RC. Memorize that. Then C is time constant over R. Time constant is 4.3. R is that. Okay, I think that I done something wrong. Why am I so careless? Ten to the power 4, 9.2 times 10 to the power 4. That one. Okay, the circuit contains power supply that provides sinusoidal alternating input voltage. AC is very popular lah. There is an output voltage Vout across the load resistor. That's the output. Is the input as shown in figure 7.1. State the purpose of the circuit is 10.1. Yep, what's the purpose of the circuit?
Rectify the full wave, I think. Full wave rectification.
Okay, rectification of
The
the
input
input
voltage
voltage
to
is
direct
still
current.
marked. So I have to say full wave, no? Full wave rectification of the input voltage, no? Figure 10.2 shows the variation of Vout with time. The load R has a resistance of 370 ohm. Show that the maximum power dissipated in R is 0.22 watt. Okay, what should I do?
The V naught square over R. 9 square over 370.
Okay, first read the maximum voltage, which is 9 volt here. Then find your Pmax, maximum power, V square over R, right? 9 square over 370, right? Because you want maximum power dissipated. That's all you need to do. Calculate out. On figure 7.3, sketch a variation with time of the power dissipated in R. Right? Very popular. Every paper have to sketch a graph like that. Oh. Okay, hi, what are they looking for? Sinusoidal shape with minima hitting at the time base. Minima there. Correct frequency and phase with maxima at 0, sorry, minima at 0, 0.2, 0.4, 0.6, 0.8, and maxima at 0.1. That one must be at 0.1, 0.01, 0.03 here, 0.05, 0.07. All maximum output at 0, maximum is 0.2. So they are required all these 3 points to get your the 3 mark. Oh. Calculate the mean power. How to calculate the mean power?
V naught is 0.22.
Half maximum power. Oh. Okay. The circuit of figure 7.1 is disconnected and R is connected directly to the power supply. Explain without calculation how the mean power now dissipated in R compares with that in B part 3. Okay.
I think the mean power will be unchanged
1 mark only. Why is the explain? Why you say it's the same?
because it depends on the current square. Mean power is depends on the current square.
Power time graph is identical. That's essentially the first point. Power
Basically,
time graph is the
it
same.
doesn't matter the
So
current
the mean
direction.
power are equal. Okay. State what is meant by a photon. Yep. All this must be by your fingertips.
Packet of quantum. No, I mean packet of quantum. Packet of quantum energy.
Just use one will do lah. Either packet or quantum of energy or electromagnetic radiation. No need to put all. Figure 8.1 shows a tube with X-rays are produced at a metal target. Okay, that's a filament. That's your X and Y. There's your metal target. There's your glass tube. There's your vacuum. And then your particles. Particles are accelerated from the filament. There's a filament to the target by a constant high potential. There's a potential across here, across the terminal XY. State the name of the particles. What is this particle? What's this particle?
Electrons.
Electron. On figure 8.1, use plus and negative sign to label X and Y to indicate the polarity of the high voltage. Okay, what's the polarity here? Which is plus, which is minus?
X should be minus.
Okay, that should be electrode. Cathode. Y should be anode. Good. An accelerating voltage of 32 kilovolt in figure 8.1 determine the maximum energy in mega electron volt of X-ray photon produced at a target. This one you have to memorize. 1 electron volt is 1.6 and 10 to the power minus 19 joule. Okay, what formula should I use?
Uh, what the- E equals QV.
That's all. Then put in, substitute in your value. Your kinetic energy of electron equals photon energy. Right? Because all the kinetic energy of the electron goes into to produce a photon energy. That's why you get maximum energy. So E equals to QV or EV. E is that is E. V is that one there. Change to SI unit. So that will give you in joule. Then you, right, 1 joule equals to that. So you divide that to get electron volt. Get electron volt. Then change to mega electron volt. The maximum momentum of an X-ray photon produced at a target. How are we going to do that? This one you have to use a formula from AS.
E equals E
Yep.
over C in joules. 0.032 times 1.6 times 10 to the power negative 13 joule.
Okay. V equals to E over C. Yeah. E is value. And C, there's your C. This value converting to joule. That's 1.6 and 10 to the power minus 19. Equivalent. Equivalent. The minimum wavelength of X-ray produced at the target. How to calculate the wavelength? What formula to use? Maximum energy given will be minimum wavelength.
E equals HF. HC over lambda.
That's your E in joule. E equals
HC over
HC over
Emax.
lambda. Right? Maximum. This one becomes minimum. Right? Cross multiply HC over lambda over E. Okay. This is your H. That's your C. E is that one, no? Incho. Explain why X-ray can be used to produce images of internal body structure that have good contrast.
The bone and surrounding tissue, different what Is it different like
Bone and soft tissue have different blackening on the film.
different blackening? Oh, okay.
Different blackening, that is your good contrast.
Therefore absorb X-ray to very different extent.
You have to use blackening to explain the good contrast. Different
Oh yeah,
blackening,
contrast.
degree of blackening. Due to why?
Okay.
The bone and soft tissue have different attenuation coefficient. Transmitted intensity by bone and tissue are very different, leading to good contrast images of. Right? 3 mark. Okay. These are alternative points. Any comment? Just memorize it.
Oh.
These days it looks like from 225, they can either cover ultrasound or X-ray. Define half-life of radioactive isotope. Okay.
Time taken for the activity to reduce to half of its original value.
Time for activity of sample to half its original activity. Okay, good. Oops, sorry. Radioactive isotope X decays to isotope Y. A sample contains only nuclei X at time t equals 0. That's your X, time equals 0. Figure 9.1 shows a variation with time t of the number of X and Y as the sample decays. We're supposed to observe that these two are observed, right? Nearly full lah, right? Nearly reach the top there. 2 square before the top, 2 square before the bottom. So we can conclude that there is only X and Y only. Y is stable. State the name of the quantity represented by magnitude of the gradient of line X in figure 9.1. Yeah.
Activity of X.
Say again.
At the time t. Wait, say what? State the name.
State the name of the quantity represented by the magnitude of the gradient of line X in figure 9.1. 10 more minutes.
What do they mean, the name?
Activity at time.
Oh yeah, activity.
This number. Then they want to know the represent by the magnitude of the gradient at line X. That gradient to the curve. Okay. That's why we have gradient is dn dt. Right? Gradient is the activity. State 3 conclusion about X and Y, X or Y that may be drawn from figure 9.1. Conclusion can be qualitative quantitative, use the space below for any working that you need. Yeah, they provide space for you to do your working, but they won't mark your working. They will look at the answer. Yep. Our conclusion.
What is stable isotope?
Both are stable isotope. Okay, good point. First point. Because why you can see there? Why nearly reach the top, 2 square below? This one X nearly reach the bottom, 2 square above. So it means that Y is stable lah. If not, Y will decrease also lah. Okay, second, 2 more points, 2 more conclusion.
So like decay constant is 0.05.
Okay, you can say about decay constant, half-life. Then third point.
Total number of nuclei is constant from the graph.
Yeah, at any time, total number of nuclei is constant, okay? Y is stable isotope. Y is a stable isotope. Total number of nuclei is constant. Half-life of X is 13.6 seconds. Right? These are other points that you can mention. You mention decay constant, okay? So it means that you need to know how to calculate the others also lah. Right? Decay constant, number, right? Number of mole that divided by 6.02 times 10 to the power 23, Avogadro's number. Activity at time equals 0. Right? That's your lambda. That's your number at time t equals 0. Okay, it's all written there. Mass of isotope X in sample B is 7.3 times 10 to the power minus 4 kilogram at time t equals 0. Determine the nuclear number of X. What should I do?
Nuclear number equals molar mass grams. So Na over N times M.
Mass of one nucleus is M divided by N, no? Right? Mass is this one. Number is this one given there. Right? So there's one mass. Then divide by mass of one nucleon is 1.66. Okay, from the data sheet. Mass of one nucleon is there. Then mass of nucleus divided by mass of one nucleon. Get 11. No? Okay.
Yeah.
State what is meant by luminosity of a star.
Total radiant power emitted by the star.
Total power of radiation emitted by the star. Explain how a standard candle in distant galaxy can be used to determine the distance of galaxy from an observer.
observer measures the radiant flux intensity received, and the distance is calculated from the formula F equals L over 4 pi d square.
Standard candle has no luminosity. That means you can measure it on Earth. Measure the radiant flux intensity. There's your F. Then use the formula, you know F, you know L, they can calculate D. Okay, good. The sun has a radius of 6.996 at 10 to the power 8 meter, and a surface temperature of 5780 Kelvin. Light from the sun is observed to have a peak intensity of wavelength 501 nanometer. Calculate the luminosity of the sun. Give your unit for your answer. Give a unit for your answer. What formula to use?
Or L equals
Yep, L equals to what?
4 pi times 5.67 times 10 to the power -8.
Okay, there's a formula given.
And then
Just use the formula. Substitute in the value.
times radius square, and then times
There's
T
a
power
distance
4
square.
temperature.
And this one can get from data sheet. Sigma. Temperature is that one there. 10 to the power 4. Straightforward calculation. Substitute only. Another star emits radiation that has a peak intensity and a wavelength of 624 nanometer. Determine the surface temperature of the star. What should I do? What formula do I use?
Lambda max T equals constant.
Now next time, absolute temperature is constant. Then call this one the second one T2. That's lambda 2. And substitute in the value. Okay, anytime may be cut off already. Any comment? If not, carry on.
No.
Okay.
Done.
Anything to comment? Since we don't have much time, anytime it will cut off, no point in starting fresh.
Yeah.
Take 15 minutes off.
Okay.
Okay, if
That's
not,
it.
we'll stop here.
Okay. See you in 15 minutes, Jeff.
Okay, see you in 15 minutes time.